So, take-home quiz. Oh, that's block B. That's block B. There we go. This was all in a nice linear straight line kind of a deal. After Christmas, I'll be giving you one with lots and lots of collisions at angles with cosine law stuff. Someone needing their glasses? Oh, can I help you out with that, my friend? Here we go, now that I've dealt with that. 112 kilogram football player running with a speed of 4 meters per second tackles another player. What impulse must the tackler give to the other player in order to bring him to a stop? So impulse is change in momentum. We have two definitions on my formula sheet for change in momentum. We have force times change in time, or we have, the rant that I've done all year, what's change in anything, final minus initial. That's not on my formula sheet. Do you see a force or a time mentioned in this question? Then I'm pretty sure I'm going to use final minus initial. And do you see angles? So I'm going to assume nice straight line. It's going to be the final momentum minus the initial momentum. Oh, and I think the final momentum is 0 because stopped. Minus mass times velocity. Mass 112, velocity 4. You get negative 448 kilogram meters per second. The question, by the way, I think said, did it say impulse? Oh yeah, it said impulse, so negative, 2 marks, including the negative. Chase is going to shut the door behind him because he has good manners. Mm-hmm. 2 marks. Number 2, what is the magnitude of the impulse? Since it's asking for the magnitude, I won't care if you said negative or positive. It's just asking for the magnitude of the impulse needed to change the speed of a 10 kilogram body from 20 meters per second to 12 meters per second in a time of 5 seconds. They're asking me to find the impulse. Now, they did mention a time in here. I started to think maybe they wanted me to go force times time, and then I said, but I don't see a force anywhere. And then I read part B, and I said, I think they want me to go change in for part A. And then once I've done that, part B, I can use F delta T and solve for F. So I said, impulse is going to be momentum final minus momentum initial, which is going to be mass V final, 12, minus mass V initial, 20. And I get I can do that in my head. That's 120, take away 200. Do you get negative 80? I guess technically I should put a dot there to go to 2 or 3 sig figs, kilogram meters per second, or 80.0. Again, if you left a negative off, B. Now they want the average force. Well, my other definition for impulse is force change in time, which means I think the force is going to be impulse divided by the time. It's going to be negative 80 divided by 5. I think I can do that in my head as well. Negative 80 divided by 5 is negative 16, yes? Newtons. Again, if you left a negative off because the question said magnitude, I don't care. Okay? Fascinating, shut up. Number 3. Graydon, is there a collision in number 3? Yeah. This is a job for momentum. Are there funky angles in number 3? So no cosine law. Okay, this will be a little nicer. I'm still going to start out by saying the sum of all the initial momentum equals the sum of all the final momentum. Before the collision, what's moving? Mass 1, mass 2, or both? Just mass 1? They collide after the collision. What's moving? Mass 1, mass 2, or both? Both. Stuck together or separate? What was the fancy word for stuck together? Do you remember? Was it elastic or inelastic? Elastic, rubber band, bounce apart. Inelastic sticks together, yes? It's an inelastic collision. Momentum of both. Final. Angles? No, then I can go straight to cross multiplying and doing the math. It's going to be mass 1 V1 initial equals mass 1 plus mass 2 V final. The final velocity after the collision is going to be mass 3.2 times 1.2 divided by mass 1 plus mass 2, 5. Could probably do this one in my head in a pinch if I needed to, Mr. Forget it. I'm going to be lazy. 3.2 times 1.2 divided by 5 equals 0.768 units meters per second. If you got that, you get 4 out of 4. Otherwise, I'd give you 1 mark for that, 1 mark for that, 1 mark for that, and 1 mark for the answer. Can you give yourself a nice clear score out of 10, please, making sure your name is on the quizzes? And once you've done that, pass them inwards. You have a loser's life if that makes your morning. Lesson 7, it says, problems involving momentum and energy. What we're going to look at are questions where, situations where, there is a collision, wham, momentum. Oh, but also a change in height, energy. And that's why I've been going on those rants for the past couple of weeks. Change in height, energy. Collision, momentum. Both, then both. Both more than once? Well, okay, then you may be doing something more than once. So the key idea here is you're going to apply momentum to collisions. And then it says use energy or, get rid of that, Mr. Duke. Cross out the word or. Use energy to analyze pendulum or curved ramps, specifically change in height. And then break it down into steps. Here's a great example. I alluded to this last day. This is called the ballistic pendulum. Before the advent of radar, before the invention of electronics, when you had to base everything on human reaction time, how could you calculate how fast something was traveling if it was as fast as a speeding bullet? Well, you would set up something like this. So here we have a 20-gram bullet. It's going to be traveling at 100 meters per second. Actually, can you cross out the 100? Make it 200 meters per second, because the 100 gives us a really small answer. I made up some bad numbers. It's going to hit this block, which is at rest. When they stick together, the bullet is going to give some energy to the block, and they're going to swing up together. So we have two things here, collision and then change in height. Momentum conservation, energy conservation. So in this problem I wrote, we must recognize there are actually two events, collision, swing, energy. Fact. Let's do that. Let's analyze the collision first. Why? Because it happened first. The sum of all the initial momentum equals the sum of all the final momentum. Look closely at my stick figure diagram of the collision. See any angles or yuckiness? Now you do in the swing part with the energy. Energy is a scalar, who cares? In this section here, do you see any yuckiness? No. Well, that means we can go straight, mass 1, V1, we can do our straight multiplication, cross multiply, and away we go. Before the collision, what's moving? Mass 1, mass 2, or both? Now normally I'd say mass bullet, and I'd use momentum B, but they also called it ballast or block of wood. They're both B's. I'm going to call the bullet mass 1, I'll call the ballast mass 2 in our traditional. So before the collision, who's moving? Mass 1, mass 2, or both? So we have momentum 1 initial. Wham! They collide. After the collision, what's moving? Mass 1, mass 2, or both? Both. Stuck together or separate? If they were separate, I would have momentum 1 final plus momentum 2 final. Still doable. This is going to be mass 1 V1 initial equals mass 1 plus mass 2 V final. In fact, V final is going to be mass 1 V1 initial divided by both masses. How big was mass 1? How big is the bullet? What's its mass? And don't give me an answer in grams. How many kilograms? 0.02? and the velocity I think I said was 200. And Dylan, what was the mass of the block? What was the mass of the bullet? Can you add 4 and 0.02 in your head for me, please? Thank you. Hey, folks, after the collision, what's the final velocity of these two stuck together after the collision? Sorry? 0.995 even? Because I'm not done, give me a few extra sig figs if necessary. 0.2 what? Okay, so sure. I'll carry a few extra sig figs meters per second. Because this question wasn't asking me to find the velocity. If you look at the diagram, h is the variable. They want me to find how high these guys swing off together. Did I just refer to a change in height? This looks like a job for conservation of energy. Kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Courtney, does the question mention heat at all? Nope. Oh, any of these? 0. Even though we're not on the ground, one of the nice things about energy is we can let the ground be wherever we want to. Let's let ground height be right there. Physics is still going to work. Any other? 0. KEI, you're saying it starts out at rest? I don't think it does. We're looking at this situation right here. I don't think it could possibly be starting out at rest, because if it was starting out at rest, I'm pretty sure my before and after picture would just look like it hanging. Why kinetic energy final? Because at the top of its swing, how fast is it traveling for a split second? In fact, Zach, what I really get is this. A half mv initial squared equals mgh final. And oh, look at that! The masses even cancel. I'll take that. I'm trying to find the final height. That's the variable in the question that they gave me. I think the final height, if I get it by itself, is going to be vi squared all over 2g, yeah? What's VI? Zach, not 0. Wait, what is VI? It's V final after the collision, Zach, isn't it? The bullet hit the block, and now they both have a combined velocity, and they're going to swing up. So my final, and you're right, Zach, the tricky part with this is your final in one section becomes your initial in another section. Yeah, it's going to be 0.99502 squared divided by 2 times 9.8. In fact, Sebastian, I'm going to use the number still stored on my calculator, square that, so that way I don't even have to worry about the rounding off issue. How high does this swing up? Not very. I think you get 0.051. If I go to 3 sig fig, like 0.055 or something like that, yeah? 5 centimeters. But measurable. You know why it doesn't swing up very high? Because even after doubling the velocity on the bullet, I'm still low. See, I changed this because I went, wait a minute, 100 meters per second, I could fall, that means it travels a football in a football field length in 1 second. I could follow that with my eyes, and I'm pretty sure I can't follow a bullet with my eyes. In fact, I even think 200 meters per second might be a bit small. But be that as it may, here's what they used to do to find the speed. If I told you the height, if you knew that, could you find that? Yeah. It'd be 2gf square root. Now that you know that, you knew this, because those were the same values. Yes? If you knew v final, could you find v initial of the incoming bullet from this equation? Oh yeah, it would be this times the V final that you got from over here divided by the mass of the bullet, and I'm left with the incoming velocity. There you go. It wouldn't be perfect because we've ignored heat, and in real life, when a bullet hits a block of wood, it deforms the wood quite a bit, generates some heat. Although if you really want it to be really accurate, you could measure the distance the bullet penetrates, and you could go work equals force times distance and probably come up with a good estimate of how much energy you lost to heat. Or you could use something that doesn't deform as much as wood does. So for example, I have a friend of mine who teaches physics, and he does this in class. He has a big sportsman's bird-killing slingshot, big sucker, and he fires it into a big ball of clay, which deforms quite nicely, which doesn't generate much heat, and the whole thing swings up, and he can calculate his initial velocity. I don't trust myself enough to fire something at that kind of a speed in the classroom without breaking something. But yeah, this was the ballistic pendulum chase, and this is how it was done. Roughly. I'm simplifying, but roughly. Now we got electronics and fancy schmancy radar and stuff. Okay, fine. Turn the page or next page over. Example 2. Example 2. Kevin, do you see a collision in example 2? I'll give you a hint, Kevin. Look up. Since it talks about collisions. Do you see a collision in example 2? Do you see a change in height? This is a job for both momentum and energy. It looks like what's happening is we have mass 2 and mass 3 at rest. We're going to give mass 1 a push. It's going to collide into mass 2. They're going to stick together. When they collide, I think it's going to slow down. They're going to slide up a hill. That's a change in energy. I think it's going to slow down. And then they're going to collide with the third mass and stick together. I think they're going to slow down. I think there's 3 things going on here. Collision, change in height, second collision. See it? Let's be really, really clever. How about we call this first collision, collision A. Here's situation B, and then the final collision is situation C. Situation A, first collision. Situation B, change in height. Situation C, second collision. Situation A. Is there a collision? Yeah, this is a good job for change in momentum. Ooh, is it in a nice straight line? Yeah, no angles. Let's see. We're going to try and see if we can take a shortcut. I'm not going to write the sum of the momentum initial equals the sum of the momentum final. I'm going to see if I can go straight to the final equation. Before the collision, what's moving? Mass 1, mass 2, or both? Mass 1. And it does say that all masses are the same. So even though there's a mass 1, mass 2, and mass 3, I'm just going to use the letter M because they're all the same. So we have M, V1 initial. They collide. After the collision, what's moving? Mass 1, mass 2, or both? Both. Stuck together or separate? So it's going to be M plus M. What's a cleverer way to write M plus M? 2M. V final. Oh! Because all of my masses happen to be the same, what happens this time for the first time in this unit? What do you notice? Masses cancel, and in fact, the final velocity is the initial velocity divided by 2, which now that I think about it makes sense. What is my initial velocity? What does the question say? 32. How much momentum does that have? 4 times 32. You hit another 4 kilogram mass, you double the mass, I think your speed would have to drop in half. That makes sense with conservation momentum, yes? So I'm good with that. It's going to be 32 over 2. The new velocity is, they move off at 16 meters per second. And they hit a hill. Change in height, energy. Situation B. Kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Any of these 0? Any of these 0? One of them is. PEI? Prince Edward Island? Kinetic initial isn't 0. That's why it's getting up the hill. And I don't think it's coming to a stop at the top of the hill. In fact, I'm pretty sure it's not, because it implies there's another collision going to be occurring, and it's at the top of a hill, so it can't be potential 0. Okay. We would get a half mv initial squared equals a half mv final squared plus mg h final. Oh! Again, masses cancel. That's kind of nice. And I, again, would do my trick of times by 2, times by 2, times by 2, because the 2's and halves will cancel. I'll get vi squared equals vf squared plus 2g h final. What do I want to find here? Final velocity. So I think I'd minus 2gh and square root. Yes? V final equals V initial squared minus 2gh square root that whole sucker. It's going to be 16 squared minus 2 times 9.8 times, what was the height? 0.82? Is that it? Yep, there it is. Okay. At the top of the hill, after the collision, how fast are we traveling? $230. Oh, square root, Mr. Duke. Do you get 15.489? 15.49? By the way, I knew the answer had to be less than 16 because you were going 16 at the bottom of the hill. You better slow down at the top of the hill. 15.49. Now, if that was my final answer, I'd go to 2 or 3 sig figs, but it's not my final answer. This whole process has been, we want to find out how fast they're moving after the second collision. How fast they're moving after the second collision. How fast they're moving after the second what, Sam? That sounds like a job for momentum. C. Since this one's a bit more complicated, it's got 3 objects. I'll go a little more systematically than I did in example in section A. Before the collision, what's moving? Mass 1 and 2. Mass 3, or all of them? After the mass 1 and 2. After the collision, what's moving? Mass 1 and 2. Mass 3, or all of them? Stuck together or separate? So we're going to have something like this. The momentum of 1 and 2 initial equals the momentum of all of them final. Is that okay, Brett? Momentum is what times what? And we did say that all 3 masses are the same. So instead of saying mass 1 and 2, I'm going to say 2m initial velocity. Right? Wham! They collide. Now they stuck together. I have mass 1, mass 2, and mass 3. But since they're all the same, what would be an easier way to write mass 1, mass plus mass 2 plus mass 3? 3m v final. Oh, and once again, because all of my masses are the same, I noticed something. What cancels? The masses. And in fact, I get this. The final velocity is 2/3 of the initial velocity, which again kind of makes sense because we had two masses of momentum going in. We added a third one. We are going to slow down by what fraction? How about by the ratio between your before and after masses? Sure, that I can live with that. It's going to be 2 times 15.49 divided by 3 times 2 divided by 3, and I get 10.3 meters per second. Lovely. Turn the page. I like example 3, I like example 3, I like example 3. Example 3 is a nice question. Why? Roller coasters! In fact, I liked it enough that I was willing to humble my pride and actually try and draw a picture and subject my artwork to your ridicule and scorn. Because that is the limit of my artwork. Now you know why I imported all those stick figure diagrams from my friend who typed up these wonderful handouts. Here's what we have. A roller coaster at the top of the first hill has an initial velocity of 8.6 meters per second. It rolls down a track. With a height of 18 meters, it strikes a second roller coaster, same mass. That has an initial velocity of 2.4 meters per second. They stick together and continue up the next hill. How high can the roller coasters reach? Can you see from here to here, change in height? Energy. Here, collision, momentum. Here, change in height, energy. Okay. However, I think everything is in a nice straight line during the collisions. It's not a nice straight line during the energies, but Rob, do I care? Why? Because energy is a scalar. Sheesh. Hopefully you're starting to appreciate why I like energies so much. I mean, if it wasn't, You know what? Let's use our same notation. Let's again call this situation A. We'll call the collision situation B, and we'll call this situation C. How many of you have ever been to Knott's Berry Farm? There's a ride called Montezuma's Revenge. You have? It sort of does this. Now, there's no collision, but what it does is it shoots you through a loop-de-loop and then up a high tower, and you go up, 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 slowing down the entire time. You come to a stop at the top, and then what? You roll back through it backwards. Right? And there used to be a ride at Six Flags called Deja Vu. I think Knott's Berry Farm bought it recently. So I went on it in 2005. What it did was the same thing, but it was a longer ride. It shot you through a bunch of loops, and then you ended up at the top of a tower. And then the reason it was called Deja Vu is now you're doing the whole thing all over again. You would go through it backwards, or through all the loops, go past through where you got launched, go up another tower, and then come back to where you started from. Any of you been on those? Yeah? Yep. At Six Flags or at Knott's? Yeah, because I don't think it's there anymore. I was there a couple of years ago, and I think it looked like Knott's bought it. So they are doing some of this in rides, Alejandro. No collisions. Oh, there is a ride where there are lots of collisions, and it's still one of your guys' favorite rides, especially because most of you didn't have your licenses until recently. Which one? Bumper cars. Those are great examples of conservation momentum. The only issue is the floor has so much friction, you really only get the full conserved momentum effect for a split second, and then your kinetic energy gets bled off into heating up the floor. Oh, you've been on those bumper cars, you hear those wheels squealing all the time, you see rubber skid marks on the floor. Yeah, you're bleeding a lot of energy to heat, and a lot of the energy goes into deforming the bumpers of the bumper cars. But this would be, I'd go on this ride. The collision would be pretty intense, but I'd go on it. Situation A. Energy. How do I know energy? Change in height and a yucky curved path. Are any of these 0? Oh, potential energy final. That's nice. So we're going to get a half mv initial squared plus mgh initial equals a half mv final squared. Once again, Joe, yay, masses cancel. And I'm going to once again times by 2, times by 2, and times by 2 to get rid of those yucky halves. That's going to give me v initial squared plus 2gh initial equals v final squared. Oh, I can find v final now, just square root. V final is going to be the square root of 8.6 squared minus 2 times 9.8 times 18. Did I type something wrong here, Mr. Duke? What did I do wrong here? Why am I getting a negative? I didn't put a negative 9.8 in like an idiot, did I? No, I didn't. Potential energy. It's a plus, Mr. Duke. You're right, I wrote it down wrong. That's just a plus sign there. Duh. It was negative, it was a minus sign in the previous question because we were finding a different velocity. Oh, square root, Mr. Duke. And I get I'll go 20.658. I'll carry a few extra digits. Meters per second. Is that okay, Kimmy? That's how fast it's traveling when it gets to the bottom. Now what? Bam! It collides. There's a collision, right? This is a job for momentum. Before the collision, what's moving? Mass 1, mass 2, or both? Mass 1. After the collision, what's moving? Mass 1, mass 2, or both? Both. Stuck together or separate? Hello? Stuck together or separate? Stuck together. Are both masses the same? This one again. So you know what? Just because it was so nice when stuff canceled, I'm going to again let the mass just be m. So I'm going to get this. M v1 initial equals m1 plus m2 v final. Yo. Ah, the second roller coaster is also moving, Mr. Dewick. Nice try. It's going to be mv1 initial plus mv2 initial, and that's going to equal m plus m v final. Yes. The second roller coaster is moving. It does say it's got a velocity of 2.4 in the picture. It's my mistake. I'll never listen to Cole again. What am I trying to find here? V final? After the collision? Sure. Which is going to be m v initial plus m v2 initial, all divided by 2m. In fact, really, the masses cancel. I could have canceled them up on this previous line because this is really a 2m. Dope. Let's try that again, Mr. Duke. This is really a 2m, and I could have said, hey, the masses cancel. You get add the velocities and divide by 2. 20.658 plus, what was the second car traveling at? 2.4 divided by 2 plus 2.4 divided by 2, and I get they move off at 11.53 meters per second. Now what? They hit a hill. Change in height? Yep. Energies! In situation C, are any of those 0? Comes to a stop at the top because it said how high can it reach? Any others? Starting on the ground. Oh, this is a much nicer equation. This is going to be a half mv initial squared equals mgh final. Once again, Shashan, if we ignore friction, the masses cancel. Explains why you don't have to get onto a scale before you get onto a roller coaster. And to find the final height then, kiddo, it's going to be final height is v initial squared all over 2g. 11.53 squared all over 2 times 9.8 squared all over 2 times 9.8. And I get 6.78 meters per second. Meters. Thank you. Check my units. So you can expect on your test, I'm going to give you one on the written section, combined energy momentum question, but it'll be everything in a nice straight line. No cosine law combined with energy. There is a couple on the big review package and in your homework, because I don't mind giving you homework that's tougher than you're going to see, so you find the tests easier. Turn the page. Football. Who watches football here? A few of you? Okay. So we have a 100-kilogram fullback. I've made up some nice round numbers on purpose. And he's running with a football at 2 meters per second. He's met head on and he sticks to the tackler, inelastic collision. Which tackler is more likely to stop the fullback? A 200-kilogram lineman moving at 1 meter per second, a 50-kilogram cornerback moving at 4 meters per second, or both the same? And convince me. Cole. Cole says both the same. Convince me.
Mass times velocity is the momentum.
How much momentum does the running back have?
Fullback.
The fullback?
200.
200. So to bring him to a stop, how much impulse must we give him? Negative 200. How much momentum does the lineman have based on these numbers? 200. How much momentum does the cornerback have based on these numbers? Okay, so we would say this. The change in momentum is equal to 200 kilogram meters per second for each player. So, Brett, it's going to be the same. It's going to be the same. You play football, yes? Okay. So, let's go to B then. They both bring them to a stop. Which tackler will cause more hurt? A 200-kilogram lineman moving at 1 meter per second when he brings the fullback to a stop, or a 50-kilogram cornerback moving at 4 meters per second, or both the same? And convince me. You've played. Which of those would you least want to get hit by? Really? I think you're wrong. Not with those, with the numbers that I've cooked there. Cole said lineman. I think he's wrong. Yep. Okay. See, Nico has recognized momentum's what brings you to a stop. What hurts you is absorbing the energy. So, how much kinetic energy does this lineman have? A half mv squared. Can you quickly crunch that on your calculator? 100? Okay. How much kinetic energy does this cornerback have? If you go a half mv squared. Sorry? 400. I'm going to tell you right now, that's going to hurt more, because where does that kinetic energy, well, first of all, after the tackle, what's his kinetic energy after the tackle? You know this. Zero. Where'd it go? Into deforming the running back's ribs. You watch football. Who gives the biggest hits in the highlights? The big, slow offensive linemen or the quick-moving players? Now, the freaks are the ones that have big mass and big speed. There aren't many of them. No, not on offense, on defense. What position has big mass and big speed? You have those occasionally freakishly athletic linebackers that have nearly cornerback speed. Lawrence Taylor was really one of the first ones back in the 80s. He was the first person anybody had ever seen who was as fast as my little guy, but stronger than my strongest guy. Now what? And in fact, it's reaching the point where, certainly in the NFL, where the athletes are a little bit larger than in the CFL, that kinetic energy has gone just past the threshold of safety. You're seeing more and more concussion issues. You're seeing more and more permanent health issues. You talk to any NFL player, and they know that if they play for 8 to 10 years, by the time they're 45, they'll be happy if they can walk without a cane. They understand they're giving up the rest of their life in major pain for this brief moment of success and money. And read some retirement articles on a lot of the defensive football players that made lots of tackles and the running backs that absorbed them. Earl Campbell is a great example. He was a running back in the 70s, a little guy who was famous for running through people. He can barely walk now. He's in a wheelchair. He's had surgery. He's had his ankles fused, and I think now he can walk with a cane. But for the longest time, you'd see him a couple of years ago. The NFL ran, Sports Illustrated ran a poster of the best running backs, so of all the Heisman winners, because he won the Heisman. And you see all these guys standing, and there's Earl Campbell in a wheelchair, ankles grotesquely swollen because you can't even put shoes on properly anymore. So it's happening.
Yeah,
Right.
average age is a lot less too. That way younger.
Yep. What's the average length of an NFL career? Do you guys know? No. It's 1.5 years. Yeah. The ones that you follow stay for a while. The vast majority of them don't, and it's most of those linemen because they're blowing knees all the time in the trenches, and nobody cares about the linemen. But yeah. Okay.
Wasn't Earl Campbell big though?
No, he was 5'9". Five.
His
If you see him, his thighs were like this.
34 inch.
Yeah, yeah, and that he had a low center of gravity, which was why he was so tough to bring down. But in terms of his mass and size, he was a little guy, but he had some of the most impressive. If you ever see a slow motion video run from the 70s and it's grainy, and the running back is shedding pads and jerseys because people can't bring him down, it's almost always Earl Campbell. They would rip his uniform off him, and he'd still be running. Yes, he's the one that headbutted, if I think hard, I'll even remember the linebacker, because it was a good linebacker too, and he put him out. But he also, if you ask him, he doesn't remember that play, because he was unconscious and staggered into the end zone, unconscious, and fell down, not remembering any of it, and doesn't remember the game. Example 4.
8 Ds, 210, and runs a 4.37.
But even he, what happened to him, Adrian Peterson, what happened to him last year? Your body's not meant to handle that kind of stress. The one that was in my generation in the late 80s, early 90s was Christian Okoye. Have you heard of Christian Okoye? Nicknamed the Nigerian Nightmare. He was 6'4", 6'5", weighed 255 pounds, and ran a 4.445. No one had ever seen anybody like that. And for 2 years, he led the NFL in rushing. He was dominant. You couldn't stop him. But his body couldn't handle it. Blew his knee twice and done. Right? We're starting to approach the limits of what the human body can handle. Football is one of the ones where you're starting to see it. Okay. Example 4. Let me give you an example of a nasty scholarship question. This is beyond what I'll ask you, but we could handle this. It says, a 15-gram bullet traveling parallel to an inclined ramp. Here's our ramp. It strikes a block. So here's the block of wood at the bottom of the ramp, and the bullet is traveling parallel to the ramp. When it hits the block of wood, what's it going to do to the block of wood? Drive it up the hill. Push it up the hill. In fact, I think on your forces test, I gave you a question where a block was sliding up a hill, and some of you said, well, how do it be sliding up the hill, Mr. Duke? Hey, maybe it was hit by a bullet. You ever think about that, smarty pants? Okay. According to this question, it slid up the hill 26 centimeters or 0.26 meters. So you know a distance. You also know V final of the block. What's V final of the block? It's meant to be obvious. Huh? 0. You could go mg down, normal force, friction down the hill, mg perpendicular, mg parallel. And I think you could find the acceleration. In fact, I know you could because I tested you on that 2 units ago. I gave you that question and you found the acceleration. If you found the acceleration and you know the distance is 0.26 and you know that the V final was 0, could you find V initial? Vf squared equals Vi squared plus 2AD. You would now know the velocity after the collision. Could you find the bullet's velocity before the collision? And as a matter, this question here is the ballistic pendulum, but at an angle, where instead of giving you the final height, I'd be giving you how high it slid up the hill. You can't use energies, sadly, because energy is not conserved. There's friction involved, but you could find the accelerator. You could find V initial that the block was sliding off at, which is V final after the collision. This is an example of what they could do to combine stuff. And you could find the speed of the bullet before the impact. If you're bored, if you have your inner nerd, if you like these kinds of challenging questions, the answer is 377. See if you can prove it. Another scholar, we're not going to solve it, but because that's beyond what we're going to be doing, but if you want to try, go ahead. Another good scholarship question. Example 5. Example 5. A 1.3 kilogram object is moving due east at 25 meters per second. It strikes a second stationary object. The 1.3 kilogram object rebounds at 9 meters per second in a direction 53 degrees north of west. What percentage of the original kinetic energy of the system is converted into other forms of energy? So here's another way to combine momentum and energy. In this question, you have a collision at an angle. You're going to be doing the cosine law. We've done a couple of those last day. But when you're done, Zach, you're going to find out how much kinetic energy there was before the collision, and that's going to be a half mv squared. You're going to find out how much kinetic energy there was after the collision. It's going to be a half mv squared plus a half this m and whatever v you find after the collision squared. And when you subtract them, you'll notice some of your kinetic energy vanish, because kinetic energy, Nathaniel, is not conserved. Total energy is conserved. Kinetic isn't. You can find what percent of the energy you've lost, what went into heat and sound and deforming the collision. Again, I'm not going to assign that, but if you want to try something nasty, if you're looking to challenge yourself, there it is. What is your homework? Number 1. What's 1b asking me to find, Alejandro?
How much work is being done?
Do they mention a force times the distance anywhere in this question? No. Do you see a graph of a force versus distance graph? Oh, what was our third definition of work? Change in kinetic energy. Oh, do you think maybe you could find the before and after velocities in the collision and then find the before and after kinetic energies and do the change in? And you know what? I think after the collision you're going to find you've lost 42 joules of kinetic energy. That's how much work was done. That's why it's negative 42. Okay? So a nice combination work energy question. Number 2, here's a ballistic pendulum. 3A. Take a look at number 5. I'm going to assign it, but I'm not here on Monday, and there's no answer, so we're going to discuss it right now. Brett, can you read number 5?
Airbags inflate very quickly when a car collision occurs. Once inflated, they deflate just as quickly. Why is this important?
Why is it so important that after the airbags inflate, they deflate? Yeah.
Maybe so that, like, because you get the shock initially, and then there's still momentum, so you're gonna like slam forwards, then you need to deflate as well.
Can you tell me in terms of energies, maybe?
I don't in terms of energy, but like when you apply force to the bag, then it's going to apply force back. So
That's part of it. I'm hitting that bag with a lot of kinetic energy. That kinetic energy's got to go somewhere. Be kind of nice if it went into deflating the bag. Now, by the way, have any of you been in a car accident where an airbag went off on you? Okay. You may notice that in the commercials, you will never see a car commercial by a car company show you an airbag inflating at speed. They show it in super slow motion. You see a gentle, rippling, cushiony airbag, and you see the person's face hit it like a pillow, like when I'm tired and sleepy and I want to lay my head down. That is not at speed. You want to know what it's like to get hit by an airbag? Let me take 2 running steps and punch you in the nose. An airbag will break your nose. It'll give you 2 black eyes. May even dislodge a couple of teeth. But you'll be alive. Now, here in Canada, we have a seatbelt culture. The seatbelt laws came into effect when I was a little kid. They made a mandatory province-wide law, seatbelts. In fact, if I'm in a car and I don't have a seatbelt because one is jammed under the seat or something, I actually will just feel weird the entire trip, uncomfortable. I even feel weird sitting on a bus where there's no seatbelt. It's part of my heritage. In the U.S., most states still don't have seatbelt laws because they're big on personal freedom. We want the right to kill ourselves. Fine. So in the U.S., the airbags are way more important. See, for us, most of us will be restrained before we go plowing into the airbags. Again, don't believe me? Watch how often sport athletes get in car accidents and you read they're thrown from the vehicle in the car accident. Why? Because they're stupid athletes who think they're invincible and they never put their seatbelt on. Dumb. So, we've discussed. We've discussed number 5. Six is good. Sorry, what? Yeah, he's got a physics background. He taught physics at Westview for a few years. Mr. Franz. Yeah, so he knows his stuff. Number 9. I'm not going to assign it. We're going to talk about it. Graydon, can you read to me number 9, please, my friend?
Why do we follow through when we make a stroke?
Quiet, please. Listen up. Go ahead.
What was that, Brett?
Read again, number 9. Go ahead.
Why do we follow? Why do we follow through when we make a stroke in golf, tennis, and baseball?
So when you play hockey or baseball or golf or tennis, when you hit an object with something else, why do we follow through? Yeah. Because if I've lifted weights so much that I've maxed my force out, but I still want to impart more change and momentum to the ball, what can I do? Lengthen the time, because momentum impulse is also force change in time. In fact, who plays baseball? Anybody here? Used to? What do you do when you bunt? What's the physics there? You're trying to reduce the time of contact as much as possible. That's why you're yanking back or not swinging at all. In fact, the best players, you watch them in major leagues, some of those guys can pull back so well, they can drop it like right at a fastball, right at their feet just about, if they need to. They can place it fairly well. Lowering the time of impact, reducing the change in momentum. You can also start, if you want to, working on the Great Big Unit Review. So on Monday, there's going to be one video lesson. It's the final lesson. On Wednesday, you'll be watching a video. You can also work on the homework during that class. Hand everything in that you want to before you go. I'll come in over Christmas break and I'll mark it. Send you an email update.